All right, if you're not excited by t-tests, you're like a normal person. Of course you're not excited. Who would be excited by t-tests? Like I said, normal people are not excited by t-tests. But t-tests are really important, and this is the first, like we talked about Z the other day, and frankly, I think I said to you guys, I used Z once in my career. That's like, other than teaching, I've used it once. I've done some science in my career. I've got one time ever when I'm like, well, a Z test would be appropriate here. It just doesn't happen. These things do, though, t-tests, right? So, oh, look, it's our friend the Z test. You like the way that came in? I thought that was kind of stylish. So to find the probability of a given value of variable. Now that variable might be the mean, or it might just be in, height. It doesn't matter what. We can transform things into z-scores and look up probabilities, or do the calculus, take the integral, but we don't have to do that because some poor bugger did that for us. Somebody did the calculus, so we don't have to do it. We then look it up in a table, or our computer does it for us nowadays very often. Frankly, I can tell you something that if I'm doing something this simple, I don't use a computer. That's ridiculous. I mean, I use a calculator, but I mean, I can, this minus this over this, I hope, it's quicker to just do it. So this is why, sometimes people say, why do you teach us how to do things by hand? Because sometimes it's faster. And also, getting the logic of it, but frankly, really, seriously, this is what I would do if I was doing this by hand, or if I was ever using this, I'd do it by hand. I don't even know if you can do a Z test in SPSS. Maybe. Anyway, the important thing is that we look it up in a Z table, everybody's happy. Yay. And it's not that interesting. We're usually dealing with means, of course, and not individual scores. Not sort of spoiled that, I guess you'd say, by saying it should be a mean. So what we're really usually interested in is how likely is this mean to happen? Right? That's what we're typically interested in. Okay. So really what we care about more often instead of distribution of x is the distribution of x bar. But remember, the numbers don't know where they came from, so they don't care that there are a bunch of means. The mean of the means doesn't care that it's the mean of means. It doesn't care that it's a weird thing that we take the mean of a bunch of means. It's just numbers. They don't know. Okay? So it sounds a little odd that we take the mean of the means. Because remember what we're doing, a sampling distribution is the average, is the all values a sample mean can take, right? So it's a distribution of the values that the sample mean can take is the sampling distribution of the mean. That's what we're going to get here. So we care about the distribution of the mean of x bar. So we do 10 people, we take their height, let's say, then we do 10 more people, always taking their heights, and then we plot all those average heights. That's what the sampling distribution of the mean is. Does that make sense, everybody? Okay. So it's a mean of means. I know that sounds weird, but again, the numbers don't know that they are. And it actually isn't that weird. Right? If I took what if I could get the average, your class averages? I could take the average of all your averages. Those numbers don't know. And I can say the average grade of somebody in 3256 is this. That sounds totally normal, right? That's perfectly simple. That's what we're doing here. Except it can take lots of different values because it's a sampling distribution. Okay, so the next slide is important. I want you to memorize it. Even though it's open book things, I want you to memorize these words in this order. This is a mathematical theorem, and words in orders, the word order matters. Okay? Given a population with a mean mu and a variance of sigma squared, the sampling distribution of the mean will have a mean of mu sub x bar equals mu, and a variance of sigma squared over n. As n increases, this distribution approaches normal no matter what the shape of the parent population distribution. Okay. It's quite possible this is question 2 on the quiz on Thursday. So memorize this. That was a big freaking hint, guys. Okay? That's part of it. Question 2, question 1. If I printed them yet, maybe I can change it. This is on the quiz. This is important, okay? I don't usually tell you something like that, but I want you to memorize this. It's very rare when I say memorize things word for word. Do that. This isn't that hard. You must have memorized other things in your life, right? You have to still memorize Shakespeare in school. I make you do anything in school anymore, I can still say, "Grams thou art and Cawdor, and shalt be what thou art promised." Of course, that's Lady Macbeth. I did it like a guy. It's only like 6 words, not that impressive. And I hated doing that in like grade 12 English. I was like, why do I have to memorize that? And actually, it's stupid that I didn't memorize it. But I can quote one thing. Well, more than one, but that's the one non-famous one. We can all say to be or not to be. Let's break this down. Let's look at this a bit and see what it says. So it says this, remember the sampling distribution, that's the mean of the means, that's just the value the mean can take. We'll have a mean of mu. Given with a mean of mu and a variance of sigma squared. They're just symbols, they're placeholders, okay? The sampling distribution of the mean, so that average of the averages, will have a mean of mu. Oh, the sampling distribution of the mean will have the same mean as the population. Of course it will. Right? Just think that through a bit. If I was sampling, again, 10 people every day, or every day, if I was sampling 10 people at the university, measuring their heights, let's pretend that the average height of the university student is 175 centimeters. Some days I'm going to, by dumb chance alone, get all the men's basketball team. And they're too tall. Someday I'm going to get a bunch of short people. Whoever, I don't know what sport short people play, so I can't pick a thing. But usually what I'm going to get is something around the average. So it makes sense that I'm, on average, I'm going to get around 175. Same thing here. Now, I think most people have no trouble wrapping their heads around that. I think. The variance is harder, but I talked about this the other day. If you think about the variance, what did I do with Victoria's marker? There it is. If you think about the variance when you actually are looking at the whole population, if you sample the whole population every time, all LW University students took their heights, what's our variance going to be of the mean? It's 0, because we get the same number every single time. So if I sampled everybody, I'm going to get 175, 175, 175, 175, what's that? It's 0. The variance of a whole bunch of numbers that are the same is 0. Does that make sense? Yes?
Yes.
Very good. Okay. So, well, if it's 0 when I have the whole population, of course it is. So there's our variance. But our variance of our sampling distribution is going to be 0 if we have the whole population. So it depends on the number of observations. The more observations there are, the less variance there is in the sampling distribution. In fact, to the point where as n approaches infinity, in other words, as the number of observations approaches infinity, this actually equals 0. Okay? So I hope you can see that. That you may not know that terminology with limits and an n and an arrow and an infinity sign. You should have learned that in high school, but you did too, by the way. Well, mostly forgotten it. I'm sure you they still learn it. God, I hope so. I have no idea what they do in high school because I have 2 kids that went through high school, but they both went to weird programs that weren't the regular ones. I just don't know. My daughter did the IB program at Cora, and I think, in fact, it was harder than first year university. Her math test looked like it was good. Anyway, this is important, right? So as the n gets bigger, this gets to be 0. So that's telling us that we're going to get a more accurate estimate of the mean the more subjects we have. Oh, of course we are. We get a better and better estimate, smaller and smaller variance, as number of subjects gets bigger. But there's something else here. Before I get to the part that's in bold, that's I obviously think is pretty important. Questions about that? Does that make sense? Questions? Okay, you're good? I don't want anybody to feel like they shouldn't ask questions, because frankly, this is the hardest course in our program. So you're gonna have questions. It's totally cool to ask them. You know what's not a good idea? Not asking questions when you have them. Okay. Something I've noticed in the last few years is people ask fewer questions. Either I'm getting way better at this, which isn't the case, or it's something to do with the audience. Anyway, whoa. As n increases, the shape of the population, of the distribution of the sampling distribution of mean, the shape of the sampling distribution of the mean approaches normal. Holy Christmas, that's wild. The part that's weird is no matter what the shape of the parent population distribution. Okay, there's a couple of ways I can prove this to you. One of the ways is I can do a bunch of math, and I'm not going to do it. You could do it yourself. You could try doing a population distribution yourself. Here's one thing you could try on your own. Don't do it now. First of all, because I don't think anybody brought any dice with them. There's usually one die in here that goes, well, I always carry a 20-sided die. Oh, you're one of them, are you? Believe me, I got lots of friends that play that stuff. It's totally cool. I make fun of all people, especially people who play Dungeons and Dragons. But it's fine. It's not my scene, but it's totally cool. But if you roll the die, I don't know how many times. What's the average die roll? Let's start with that. Six-sided die, not one of those 24-sided. Oh, you know, I'm going to roll for my hit points. What's the average roll on a 6-sided die? I'm not going to tell you until somebody answers me. The podcast might be a little bit quiet today.
3.5.
Thank you. 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6 is 3.5. Right? The average roll on a single die is 3.5. Okay. Good. Okay, we're going to roll a die. We're going to roll it 10 times. Roll it 10 times. And what do we expect to get for our mean? We're going to do this a bunch of times. What do we expect to get? Let's use this again. So we expect to get 3.5, as Carter said. 3.5. Most of the time we'll get something around 3.5. Sometimes we're going to roll, let's say we're doing 10 rolls. Sometimes we'll roll 10 ones. It's going to happen. So our average is 1. It's going to happen. How often is that going to happen? Not very. But it will happen. Sometimes you roll 10 sixes. It's going to happen. It's not going to happen very often. Sometimes you'll roll 9 ones and a 2. Just a little bit higher. And a little bit more likely, because there's 10 places the 2 can go. It can be rolled 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. If you had 2 2s, now it is more than a lot of places. You can go 1st and 2nd, 1st and 3rd, 1st and 4th, 1st and 5th, 1st and 6th, 1st and 7th, 1st and 8th, 1st and 9th, 1st and 10th, 2nd and 3rd, 2nd and 4th. See what I'm saying? It gets a little more likely. Same thing's going to happen on the other side. If we go 6s and a 5. It's probably going to get more like, wait a second, and a little more. Oh my God! It's a normal distribution. That's kind of neat. You can even do it with a coin. Something that has a 0 and a 1, heads and tails. You can do it with a coin. You can do it with this, anything even that's binary like that, with 0s and 1s. You'll still get a normal distribution. Of coin flips, you get a normal distribution. Of the sampling distribution of the mean, it always comes out that way. It can't not. It is a property of our universe. Okay, the world works like that. Not just the world, the universe works like that. We can totally take advantage of that, which is cool as hell. So now we know the shape of a population distribution, the shape of a sampling distribution without knowing anything about the shape of the parent population distribution. That's pretty neat. So what matters is random sampling. So flipping a coin, rolling a die, those are random. If I was measuring and pretend that I'm randomly selecting people in the university and measuring how tall they are, how high they are. Depends. At night, it's different. Thank you. Random sampling matters, and technically the reason that you end up with this nice, beautiful shape is because of randomness. But you can kind of pretend it's random and it's okay. Like, you can really not care about randomness. Random assignment of subjects to groups is an entirely different question, but random sampling, the central limit theorem is incredibly robust when you on violations of the assumption of random sampling. It can deal with it just fine. So it doesn't really have to be random. It's going to be better if it's random, but it doesn't have to be. So to find the probability of some mean, we just use the z-score. That's how this would work. We would use the z-score to find the probability of a mean, just the same way we found the probability of an individual value. I'm just going to use our old friend, the z-score. So I'll just show you how we would do this. I've got, it looks like this then. This is the regular z formula on the left here, right? This is x, it's just standard deviation units. Well, we're doing standard deviation of the mean. Well, the mu is the same. Remember, it's mu sub x bar equals mu. So, right, we just put mu there. Now, the bottom's going to change, the variance is going to change, and that changes the standard deviation, I'm sorry, because we're now using the sampling distribution of the mean, but we know what the standard deviation will be. It's the root of the variance, and the variance is sigma squared over n. So, the standard deviation is sigma over root n. So all we're going to do is this isn't a different formula. It's the same formula. One of the things I think that happens a lot of times in sort of intro level stats is you think you have to memorize a whole bunch of formulas, and you really don't. There's like 3 you have to know. They're all just variations on a theme. This is this. It's just that now we're using x bar, and now we're using sigma over root n because we're looking at a sampling distribution of the mean, not simply at a mean, or a score. All right. Does that make sense? You see what I did there? Nothing magic, just sub into a formula. Just subbing into a formula. All we're doing here. Okay, good. Good. Okay, let's. Oh yes, please, Vera.
I missed where the root of n came in. And are they the same formula, or are you modifying?
Well, it's the same formula in that all we're doing is subbing into it. So any z-score is this. That's a z-score. A z-score is the value of the score minus the mean over standard deviation. It's the score in standard deviation units. The difference is here we're going to use the mean. So we have to, what's our mu going to be? Well, it's still mu, because the central limit theorem tells us that. And central limit theorem tells us that the standard deviation of the sampling distribution of the mean would be this, because the variance of the sampling distribution of the mean is this. So we just took the square root of sigma squared over n. We get sigma over root n. Make sense? Yeah? You good with that? You okay? You sure? Okay. Everybody else? Okay, good. Thank you for asking. It's better than not asking. Okay. So it changes, but it really is the same formula. We're just subbing into it. So here's an example that you'd never do. Let's pretend we have 25 subjects. I'm sorry, participants, because apparently the word subject is pejorative somehow, and it isn't. It was a perfectly good word. That's how I was trained. And then it's like, no, it's called participants. I got a thing from an editor once, and it said, we now call subjects participants. I said, these are pigeons. They didn't sign a consent form. They shit a lot and eat food after they peck at things. And I called it, I changed this. I said animals. I'm just not calling them participants. I refuse to call Oh, I'm sure the pigeons are really, really offended that I called them subject. Anyway, these are things that really shouldn't bother me years later. Like that happened 30 years ago. Still kind of bugs me. Anyway, 25 subjects. My class, I'm going to call them subject. We're given an IQ improvement course. Almost certainly won't work. Because you could probably study an IQ test. That actually would work. So it actually wouldn't improve your IQ. It would improve your performance on IQ tests. Those are two different things. And we'll see if they end up with a mean of 110. Why do I use IQ? Because you know what? I know the standard deviation of the population, you know, of IQ and the mean. It's an easy one. There's a reason we use IQ a lot for these examples. Because the math makes the math easy. It's doable. IQ, what do we know? We know the population mean of IQ is 100. We know the standard deviation is 15 because the test is designed that way. Okay. There's not a lot of times when we actually know these values. There are not a lot of times when we know these values. Wow, I mumbled that. There are not a lot of times when we know those values. I know I talk fast, I'm sorry. There's not a lot I can do about it. I'm almost 60 years old. It's not changing, guys. When I worked in Newfoundland, when I taught Keo, I was told actually by Newfoundlanders, I was the only mainlander they'd ever met that talked as fast as they did. I don't have one of their ridiculous accents, of course. That's how we'd start all classes. I'm not from here. I don't have one of your ridiculous accents. And I thought the people who laugh at that are cool. People who don't, calm down. All right, so we know that, so we can just sub into a formula. This is going to be easy. Hey, look, here's some arithmetic. Z equals x bar minus b over sigma divided by root n. 110 was the score from the problem. 100 is the mean. 15 is the standard deviation, because that just is the beauty of IQ. That's why we use it as an example. We've designed the test that way. Oh, over root 25, that means we have, well, we had 25 subjects. Oh, I wonder why I chose 25. Do you think it might have been because square root of 25 is 5? Makes it easy? Yes. I cooked the example to make the math easy. 10 over 15 over 5, 10 over 3 is, ooh, look at the big Z score, 3.33. Anybody, doesn't matter, you shouldn't have to look up the value in a table. In fact, I bet your Z table that you have in the back of the book, I'm certain it does not go up to past 3. Because 3 is 0.003, like it's significant. I actually looked it up because my calculator just does that. It has a Z table built in, and that's the probability. And then the probability of this happening is 0.00043. Probability of that happening just by dumb luck alone. Okay. These are, you've worked on problems like this before, of course. You see how I got that? It's just something in the form you want to get. Okay. So there's an issue here. We usually don't know the variance or standard deviation for population. I know it for IQ, we all do. It's 15 unless it's the Raven progressive matrices test, and it's 16. I mean, it's one or the other. But we don't usually know that. What's the standard deviation of anything? You just don't, it's not something you know. You very often can theoretically figure out what a mean could be, but how squared out something is a lot harder. Well, the expected value of s squared is sigma squared, correct? Yes, that's why we use remember divide by n minus 1, the whole thing, to get an unbiased estimate. So if the expected value of s squared is sigma squared, why don't we take advantage of that? We could just sub s squared in for sigma squared. Obviously, that's what we're going to do, because there's nothing else we could do. But the weird thing is now we have to take account of two separate sampling distributions. There's the sampling distribution of the mean. The central limit theorem is beautiful. It takes care of it. It's very nice. We also have the sampling distribution of the variance, which is like, what? How could, yeah, well, you get a mean of a bunch of variances. The numbers don't know where they come from. You may find it weird that we take a bunch of variances and get their mean, but you can The numbers don't care. And we know that the standard deviation, and therefore the variance, will get smaller as n approaches infinity. So in other words, it will change depending upon n. We have to take that into account when we do our calculations. Right? So when the t-test was invented, the person who invented it, Gossett, thought, okay, I have to figure out how it changes depending upon n, just not how it changes depending upon x, the sampling distribution of mean. So we can't use z. We have to find a new way to do this. And what we're going to do is we're going to sub the sample statistic for standard deviation in for the population parameter for variance. And then it's not going to be a z anymore. Now it is, now this will be technically a new formula. Though it all grew out of the z formula. It all grew out of it. So I even don't think of this as a separate formula personally, because sort of not theoretically, on an intuitive level, it's all just the same math. It's just you get the values from different places. So what we do is we do this. Oh, look at t-test. This is just like a z-test, except that's an s, not a sigma. That's the only thing that's changed. We've now estimated sigma with s. This is Gossett who came up with this, who was published under the name Student, which is kind of great. Called himself Student. That's kind of cool. So sometimes you'll hear this called Student's t-test. He worked for Guinness Brewery, and he was like the world's best job doing stats at a brewery. It sounds like my dream job. If they could just throw in your podcast at all, it's like gold for me. Oh, and there's Mad Men playing. If you just do all that. So he comes up with this, and it was basically to look at, it was doing quality control at the Guinness Brewery in Dublin. And Guinness was like, you can totally publish this, but don't use your name because we don't want you getting headhunted by another company. So he published then under a pseudonym. The pseudonym is Student. So it's, like I said, sometimes called Student's t-test. But I think that's kind of great. He's like, no, I'm just a student, man. Also, I'm the head statistician for Guinness Brewery, which is kind of cool. So he does this, but he knows he has to find out how does n affect this? He knows central limit theorem. Obviously, the guy can do some math. It's not that. So he knows that'll be fine, but it's dealing with the denominator of the fraction. So if you remember that t's going to change depending upon the level of number of observations. Oh, we talked about degrees of freedom before, didn't we? Yeah. The degrees of freedom to estimate sigma squared by calculating s squared. That's how this works. To be a little more precise, it's what we've estimated. Well, we've estimated x bar to allow us to estimate s squared. Estimate sigma squared with s squared. You don't have to know anything now. Like, think about how powerful a technique this is. We don't have to know anything about a population to determine if what's going on in the population. That's really freaking cool. And it's mathematically sound. It's not like this is hocus pocus here. This is mathematically makes sense. It's not just that this isn't just gut feelings. Well, this is a really good lint free cloth, and somebody's done this with. I use them for making model planes. I have all kinds of weird hobbies, like I'm a child. One of them was making model airplanes. If you were in my office, there's all these model warplanes. And there's a whole anyway. And I'm not that great at it because I don't know if I've told you, but I can't see. So they're okay. Some of them are pretty good. Some of them are. John, can you put these two parts together? That kind of thing. Some of it's that. What's going to happen here? Well, we're going to lose degrees of freedom whenever we use t-test. We're going to lose the number of degrees of freedom the number we lose is based on how many means we estimate, basically. So it's usually going to be 1. So, does that make sense? We then look it up in a table that with the degrees of freedom. So for any situation, let's say we've got 45 subjects, and we want to see if they're different from, well, we just use height, make it the lamest possible experiment. Not even an experiment, just being lame. We're going to sample 20 people, and we're going to see if they're taller than 175 centimeters on average. I don't know why we're doing this. We have a hypothesis that psychology students are taller than average Oklahoma University students. Perfect. There we go. We're never getting this published, by the way. There's no research grants for this. Are people tall? Is not really a question. So we can do this, though. So, I don't know, let's pretend you're a random sample. I get your heights. I get 179. I don't know. Let's make up an example. 179. The average I said was 175, right? And let's say the standard deviation that we get of all your heights is, I don't know what. Somebody pick a number. Reasonable number in centimeters, standard deviation for your heights.
10.
10's good. I like 10. 10's okay. And how many people are in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19. The square root of 19. There are 19 people in this room right now. Square root of 19 is 4.4. Somebody get a calculator on? 4 divided by 10 divided by about 4.4, I think. What's the square root of
4.3.
4 point?
So yeah.
4.39?
3.5.
Oh, 3.5. You ran to 4.4. Ah, 4.35. Okay, so that's going to be, what's 10 over 4.35? That's going to be, what, 2 point what? 2.29. 2.29? So 4 over 2.29. There's my calculator. 4 divided by 2.29. 1.74. We had 19 people. How many degrees of freedom do we have? We have 19 people. Thank you, 18. Critical value of T with 18 degrees of freedom is what? Let's find out. Let's see. Critical value. I mean, I don't have my book on me. Value T 19 DF. Go. There we are. Is there. Okay, assuming I'm reading this table properly, which is not 1.74, no, sorry, 18. 1.734. That's awesome that I came up with, that we as a group came up with that's a plausible answer. Okay, so the critical value, if I read my t-table right, is 1.734. And ours is 1.74. That's awesome that we came up with something that's plausible. Okay, so you're taller than the average Oklahoma University student. Not a lot, it's very close. Critical value is 1.734, and our calculated value is 1.74. So kudos to Victoria for coming up with 10. That's a perfect, that's a really plausible standard deviation. And it is too, if you think about it, but 10 centimeters either way, it's sensible.
I'm 10 centimeters shorter than what you came up with, so.
No, but you're within a standard deviation. It's a totally reasonable guess, right? It's totally reasonable. So that's how we would do a problem like that, right? And you've done a million of those. Okay. Okay. So let's look at this for differences between groups, or two sets of groups. What do we have here? It looks like the same formula, except what I've done is I've taken some numbers and put little D's underneath them. Well, what I've done is I've taken let's see if it's before and after. So, I don't know, Can't make it any taller, so that's a bad example. I could look at how you do on quiz 1 versus quiz 2. Perfect, because they aren't the same quiz, but let's go with that. I have 2 sets of numbers. All your scores on quiz 1, all your scores on quiz 2, which you don't have yet, but let's pretend. Did you do better on quiz 2 than quiz 1? Well, I hope so. But we don't know for sure. We can find out. So we have 2 sets of scores. What we can do is just get the difference. Right? So we get Kieran's score from before, Kieran's score from after. We get Skylar's score from before, Skylar's score from after. Parthy's score from before, Parthy's score from after. We do after minus before. You can go before minus after. It doesn't matter what order you do it. So if we just, because you're your own control group, right? So when I get Kieran's scores, I just take one and subtract the other, and now I got a score for a change score. So what I've done is I've kind of, I wouldn't call it cheating, because it's not cheating, it's perfectly sound, but it kind of feels like that, because it's like, oh, I've just turned this into a 1 sample t-test. But why doesn't it subtract something on the top? Because if there's no difference, I expect the difference to be 0. So it's really, technically, it's x bar sub b subtract 0. So we just lose the 0. So again, it's the same formula.
Can you explain it again?
Yeah. No, I can't. That was the only way I could. I have no other way. Yes, of course I can. So, if we got your scores from before and after, you get that, right? That makes sense. Okay. And we can subtract them and get a single set of scores for all of you. So I'd have, did I say 19? 19 people, I'd have 19 scores. Instead of 38 scores in 2 groups, I've got 1 set of scores, 19 scores. What value do we expect the average, where did I put Victoria's marker? There it is. What do I expect the average of your score of after minus before, what should that equal? Well, if there's no difference, it should equal 0. Yeah, some, you're going to go up a little, going to go down a little, going to go down a little, going to go up a little. It's going to happen. But on average, we would expect there to be no difference. So we expect this, change that. The expected value of this is 0. You know, I could make up some kind of scenario where I say the expected, that I expect there to be an improvement of 4 points. Is it going to be more? You know what those happen in statistics textbooks. No one ever does those things. We just always assume it's 0. So if you think about the T formula, there. X bar minus V over sigma squared, or over S divided by root n. But, well, that's 0. So now it just becomes this. Make sense then?
Yep.
Yay. So technically it's minus something, but that something's going to always be 0. It's practical.
I don't get why it's 0.
Because we don't. If there's no change before, what am I pointing at the limit here? If there's no change before and after, your score should be, the difference, the change score should be on average 0.
So that, like, knowing that the expected value before minus after is 0,
Yeah.
that is like,
That's our
we
mean.
need to translate that to other things.
Yeah, that's our mean, right? So the mean that we're subtracting from here is the average difference score. Because we're trying to see if this difference score is different from 0. Has there been a change? And if there is, then we say if there was some significant difference, blah, blah, blah. But to figure that out, we have to, first of all, calculate the scores. So we take your score before and after. I just saw a light bulb, I think, go off over your head, actually. Did you just get that?
No.
No, I just saw a look. Sometimes I can see a look on people's face. They go, oh, yeah, I understand now. Maybe you were just inhaling, and I just misinterpreted. But point is, we expect, if there is no difference between these two, if there's no effect of time in this case, that you're getting better at stats, we expect that. So the average difference is actually that. mu sub d equals 0.
But that depends on the question, right?
Yes. And the
Okay.
question's almost, yes, I'm sorry. So we are talking at cross purposes here. Theoretically, yes. Can it be the case that we have something different than 0 there? Yeah, sure. It's possible. It shows up in intro stats textbooks as problems. But it never happens in the real world. I would never expect, again, if we were, let's say, are you getting better at taking my quizzes? I would never have a value say, well, I expected to go up by 3. Like, where am I getting that from? Where's the 3 come from? I expect there to be no difference if my teaching isn't getting any better or you're not getting any better at it. I expect a difference. I expect no difference if there's no effect, rather. I expect something if there is an effect. Probably getting, one would hope, getting better, not worse. I hope for positive numbers, not negative numbers.
So for the purpose of this course, we always assume that it's 0.
For the purpose of your entire career. There might be a time when you're sitting there and you're analyzing some data, and I don't know, Vera, maybe you go on and you do this and you end up doing what we all do here, and you are looking and you go, yeah, I'd expect that to be like a 5 theoretically. Yeah, then it's 5. It's almost always 0. In fact, it's so much almost always 0 that you're usually taught the formula is that. It's actually minus mu sub d, which is usually 0. That make sense?
Yeah, I'm just thinking I think last stats,
Yep.
there was an example where you see how people scored before or after therapy.
Yeah, sure. That's a good one, yeah.
So then you would expect there to be a difference.
You expect a difference, but your null hypothesis has to be there's no difference, doesn't it? Your null should be there's no difference. Now, there might be certain cases where the null would not be no difference. But I don't know when that would ever be. The thing in the right-hand side, the thing we subtract from, is always the null hypothesis. This is H sub O. It's what the mean of the population is. It's always H sub O. And H sub O here is almost always going to be 0. In fact, so much so that this is often taught as a separate formula. And it really isn't. It's actually x bar minus mu, and just at mu 0.
Now I got it.
Awesome. No, believe me, I remember learning this stuff and looking at it over and over and over, and then, like I said, then you get it. This stuff works like that. Other questions? Very good on asking, because to understand the next thing, you have to understand this thing. So, where'd my pointer go? There it is. Okay. Put that back. So this can be used then for pairs of observations. Or matching. So the matching, pairs of observations is like, if I've got your score before and after. Matching is a bit different. There are very specific cases where I would have different sets of scores. And let's say we've got a drug for, I don't know, blood pressure drug. So I got a blood pressure drug, and I want to see if it works, of course. Now, instead of taking you before and you after, because maybe there's going to be some carryover effect, what I'm going to do is I'm going to find people whose blood pressure is perfectly the same. So I take all your blood pressures, right? And I find out that Carter's blood pressure is exactly the same as Chloe's blood pressure. You are now a pair. And then I find that Kristen's blood pressure is exactly the same as Parthy's blood pressure. You are now a pair. And then what I do is I give you the drug and I don't give you the drug, and I give you the drug and I don't give you the drug. Now, you subtract you subtract you. This is assuming I just did it properly in my head. Those are pairs of observations. Those are, you're matched, okay? The thing is, you're matched on one thing, the dependent variable. Now the two groups are completely different. So it better be the case that we have something that is not going to be affected too much by anything external other than our treatment, which is our drug that my theoretical drug that I'm giving some of you. Okay? Well, we could do that. You might do that with twins. It's great with twins. It's great with litter mates generally. You think about it, actually, twins are just a litter size of 2 in humans, which is a really weird thing to think of. But it is. So if you know with rats, you might have a litter, you got a litter mates. So they're the same. Twins, they're the same. Oh, you guys, when you had same blood pressure, you had same animal. Okay? So then we can do this. I've used these quite a few times. They're very useful. For before and after stuff. Great. And I actually tend to, the thing about your quiz scores, I do that all the time to see if you're all improving. I actually analyze the data. This course has so many things that get marked. So the nice thing is I have a lot of data, so I can go in and just see, oh, are people improving? And I use these kind of, this all the time. And yes, you usually are improving. Does that make sense? This part here about matching, but remember, we've now made the 2 groups completely different, which sounds like something you should never do. We were probably talking 21 to 27 is something you should never do. You should do it only in very specific circumstances. Okay. What if your pairs aren't matched? So we didn't match you guys on blood pressure or whatever. Now we have 2 populations, maybe. That's our research question. Our null is we don't have 2 separate populations. Our alternative is we do. So our hypotheses here change a little bit. We have 2, of course, as usual, ho and ha. Ho is mu1 equals mu2. Mu2, of course, my favorite band. Never tired of that one. I've seen mu2 6 times. Pretty cool. I almost got pulled up on stage once, too, to play. They were doing the thing where they pull a guy up on stage, and I was like right up front. And my brother recorded the concert illegally. And you can hear my brother yelling, "Pick Dave." And it's like, Abe can't hear me because it's 18,000 people at Midwood Gardens. And also, I don't think Bono knows who Dave is. The Dave he knows is the guitar player because that's Edge's first name. It's Dave. Anyway, I like you too a lot. So there's HO, there's HA. I could make this directional if mu1 is bigger than mu2. I'm just gonna be a little more conservative and say mu1 is not equal to mu2. But I could make it directional if I felt like it. There's our 2 hypotheses. They're the same, they're different. Right? Okay. Now let's build the formula. Whoa. Excuse me. Okay, the original T formula looks like that. We're going to sub into that formula the stuff we know about different groups. So remember, there's the statistic that we calculate from samples. That's HO, and that's the error. What we want to do is sub the values for the statistic that we're interested in, to see if they're different, the HO values, and then the error. Okay? So that's what we're going to do. Does everybody have this? Everybody's good? Makes sense. What we're going to do now is we're just going to turn this into a formula for doing 2 groups, 2 separate groups. Just like that. The statistic that we're interested in is x bar different from x bar 1 from x bar 2. Let's put that right there. Then we're going to subtract mu1 minus mu2. Remember that our null says that mu1 equals mu2. So if mu1 equals mu2, then mu1 minus mu2 equals 0. So practically, it's just x bar 1 plus x bar 2. So it's the same thing here. Again, you could come up with some scenario where you give a value other than 0 for mu1 minus mu2, but I can't think of one. Play keyboard. Okay, so same thing happened here. Look, that's 0, so just now it's just x bar 1 minus x bar 2 over whatever the error is. So then we have to figure out what the error is. But we got the numerator, the fraction done. That was easy. The error is a little more complicated. Is that bad? All right. Okay, you see where I'm going with this? You okay so far? Okay, so what we do next is we figure out the error.
Here's a question.
Yep, sorry. Oh, sorry, I missed that. Yeah, sorry, I apologize. Bad eyes. Yep.
So this is for two groups.
Yep.
Why are we using this formula? Because we do have a formula for a t-test for two groups.
Yeah, that's two groups when they're exactly the same, when it's you tested twice or it's you and you matched up together. These are not matched up together. They're not you tested twice.
Okay.
These are two independent groups. This is called an independent sample t-test or a uncorrelated sample t-test, usually an independent sample t-test. Yeah, good question, fine question. You're right, we have something, but it's used in two groups when under very specific circumstances when those two groups are you before and you after, or you two matched up together. This is a case where we haven't done that. This is a case where I've randomly chosen, I don't know, 8 of you and given you, 8 of you could do the quiz open book and 8 of you can't. I've done that. No, I'm not doing that. Don't look at me like that, guys. Come on. I'm saying that theoretically, let's pretend that I've done that. 8 of you are, 8 of you are going to write the quiz with your notes, and 8 of you don't. And I'm going to see if it actually helps. By the way, it wouldn't help. It really wouldn't. It's too short. But there I've matched you up. And yep.
I have a question like from the slides previously.
That's fine. Yeah, let's go back.
So when we switched from z-score to t-score,
Yes.
We had standard deviation
Yes.
in denominator.
That's
And
right.
you said we switched to t-score because we don't have standard deviation.
No, we're not the population standard deviation. Yes.
Yeah, so the S is still standard deviation.
Yes,
right?
but it's a sample standard deviation, not a population standard deviation. One's a statistic, one's a parameter.
Yeah, that's
Is that good? Good. I like really specific questions I can answer quickly. Those are my favorite kind. Or the ones where I go, I don't know. Those are quick. Those are quick too. Other questions? Sorry that I went ahead without, well, I did look, I just can't see. Okay. Okay, nobody has a question now? Okay, good. By the way, don't feel bad about pointing out when I haven't, thank you for doing that, because like I actually can't see that well and it's helpful. It's when if you said it like, look, you can't see. That would be bad, but nobody's doing that. Nobody's doing that. There's nothing wrong with saying, Dave, you missed that. That's cool. I like that. I want you to do that. Okay, so don't feel like you're doing anything offensive or something if you point something out that I didn't see. Because that's who I am. I'm totally cool with it. Okay? Just want you to let you know. Because sometimes people think, oh, I shouldn't say anything because Dave can't see. I can't even tell whose mouth it came out of. Yes, okay. The error's a little more weird, but at least we got the top part. Now let's do the error. Oh, we know. I can tell you some properties of variances. First of all, these are going to have to be weighted, right? Because variance depends on the number of observations, doesn't it? It depends. The standard deviation or variance of the sample is going to depend on the number of observations. We're going to have to then adjust our, we have to weight it by the number of observations. Oh, just divide by the number of observations. Oh, and you're thinking, well, we're subtracting the two distributions. Why not? Because you don't subtract them. Just, you don't. Okay, you add them. Just say you add them. And just, it's fine. What you're doing basically is getting a weighted average of the standard deviations, and if you're doing that, you don't subtract when you're doing averages. You do it that way. So we're going to weight them. So now our formula looks like that. Oh, look! You've seen that before. You probably spent about 4 weeks with Keo going, and then if you had this problem, it's the same problems over and over and over. Or with Casey's now. Who did it? Who taught you intro stats? You probably took a week and a half doing a zillion different problems like this, and you should. And it's good that you did that, but we're past that now. But this is where the formula comes from. This is where the formula comes from. So it's the same t formula again. We've subbed values into it, but it's the same t formula. So for HO, well, it's gone because it's 0. And the error, well, they just add up. We take the square root of that because it's a variance estimate, we need a standard deviation estimate. So that's our new formula. Okay. So, is it good so far? Okay, looks like it. Okay. Variances aren't equal. Things are, well, we're going to have to do something about that. We're going to say, you think, Dave, the variances are never going to be exactly equal. You're right, they aren't. If they're really not very equal. You're going to say, Dave, how much is really not varying? Oh, let's say one variance is 4 times bigger than the other one. So if the one standard deviation is twice the size of the other one, that's usually where you draw the line. The math is very robust. It can deal with different size variances, but once one standard deviation is 2 times bigger than the other one, it kind of falls apart. By the way, it works. It's just the test becomes way more conservative. So you actually don't make a fool of yourself and say things happened that didn't, but you miss things that might be there. So if the variances are different, we use what's called the pooled variance, which is just weighted by the number of subjects in each group. How many degrees of freedom do we have?
N minus 2.
The n, like n is the total number of subjects, yes? So we have n plus 1 plus n plus 2 minus n, 2, exactly. Why did we lose 2 degrees of freedom?
Because there's 2 groups.
Yeah, and you're right. Why did we lose degrees of freedom? Because we fixed values. We fixed 2 means. We had to calculate 2 variances. Where are they? Right there and there. To calculate those variances, we had to put means in. We fixed them. If we fix means, we lose degrees of freedom. Okay. Does that make sense so far? Okay. Now, I should also tell you that when you play with SPSS, which how to do t-tests in SPSS, there are, I think, 3 videos I posted in the CMS, or LMS as we call it. When did I do that? Yes, last night, yesterday afternoon, something like that. So check those out. They're how to do t-tests on SPSS. It's very similar to PSPP. It's almost exactly the same. One of the things you'll note if you do a 2-sample t-test in SPSS is you get a thing that shows what are called partial degrees of freedom. And you look at it and go, what? How can this have 9.3 degrees of freedom? What the hell is that? It's doing a t-test in a different way. And it's actually a much more accurate estimate of the question, a more accurate answer of are there any group differences, basically. So you can use partial degrees of freedom. I don't, that's math that's beyond the scope of class. Okay. Typically people don't use that. They typically use this. And you'll also find, by the way, you look and go, oh, look, they all agree. So it's not a huge deal, but I just thought I'd bring it up. You don't usually see partial degrees of freedom in papers, which I don't know why. You just don't. So some assumptions. There's always assumptions behind the math. To make the math work, we had to assume some stuff. The first thing we assume is a simple random sample. A simple random sample. We assume that. Because the math assumed that. That's from the central limit theorem. The central limit theorem assumes that. We were subbing in x bars and s's for sigmas and all that because of the central limit theorem. It assumes independence of observations. And homogeneity of variance. We can violate the hell out of random sampling. We do it all the time, And the math is very robust. It can deal with those violations. No big deal. Homogeneity of variance. They should have similar variances. We can violate that a lot. Once one's about 4 times bigger than another, we go, that's a bit much. But actually, there's a way to deal with it, which is full variance. So we're okay. So these two, we can actually, simple random sample and homogeneity of variance, we can deal with those. We can never violate independence of observations. So if I know Vera's score, that doesn't tell me what Kira's score is. It just tells me their reading problem. Right? But I can't know one score doesn't tell the other. We can never violate that assumption. The whole thing falls apart. I think of that, and the way I remember that is, I think of that like that's cheating. I think of it like a classroom, and it's like, okay, is there an effect of where you sit in a classroom for a test? Yeah, sure. There's going to be an effect. If you sit where you're used to, you probably do a little bit better. It's just true. But the effect is probably kind of small. So that's one thing. Another one will be, think about it like homogeneity of variance. I like to think of it sort of like, is the test too easy? Or too hard? Because if it's too hard, everybody's going to fail. Too easy, everybody's going to get perfect. Somewhere in the middle, it's fine. Can I let people cheat off each other? No! And some of you have experienced me getting very angry when I catch people cheating. And that's not because of this, but I like to think of it that way. Because now I don't know your score. I know your score and a little bit of somebody else's score. That's what when the score that you give me is, oh, it's your score. It's a little bit of Skylar's score because you looked at his paper. Right? So I can't have that. That wrecks everything. So that's kind of what's going on here. Behind the scenes, what's happening is the whole thing is predicated on on the scores being based on one thing and nothing else, basically. That's the way of putting it, I guess. So you cannot violate that assumption. You can't. So if I know one score, it doesn't mean I know anybody else's score. That's all. So I always think of it as the no cheats assumption. All right, questions on this stuff. I know now we've just done 6 weeks of 21-26 in an hour and 10 minutes. But you already did 6 weeks of 21-26 when you took 21-26. Okay, now remember, the quiz on Thursday, also please come Thursday. The most complicated lecture in the whole course is Thursday. Power is hard. You get it, you'll be fine. I'm telling you though, you want to come to that one. It's pretty exciting. You'll be edge of your seat. No, you won't, but you really should come. All right, thanks everybody. Yep. I resisted chewing on it the whole time too, because I often, when they're mine, I put them in my mouth.